Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the Real-Time Anomaly Detection System, the system that finds unusual patterns in metrics, logs, and events before they become outages or customer-facing failures. We'll cover how companies like Netflix, Uber, and LinkedIn detect latency spikes, drops in stream quality, and suspicious behavior in real time. Whether you're preparing for a senior engineering interview or building observability at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the Real-Time Anomaly Detection System, the system that spots unusual patterns in streams of metrics, logs, and events before they become outages, fraud, or customer-facing failures. If you have ever wondered how companies like Netflix, Uber, and LinkedIn detect strange spikes in API latency, drops in video stream quality, or suspicious login patterns in real time, this video is for you. We'll walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FAANG interview or building observability infrastructure, let's get into it. Here is the core problem. Modern applications emit millions of time series points every minute. Request latency, error rates, throughput, queue depth, CPU, memory, business events, and security signals. Somewhere in that noise, a real problem is developing. An API endpoint suddenly takes twice as long. A microservice starts throwing 500 errors. A payment gateway sees a burst of failed transactions. A fraud pattern appears in login events. By the time a human notices the issue on a dashboard, customers have already been impacted, revenue may have been lost, and the incident response team is scrambling. We need an automated system that continuously monitors high-dimensional streams, separates normal variation from true anomalies, and triggers alerts within seconds or minutes, not hours. Let's walk through the functional requirements. First, the system must ingest diverse data sources. Metrics from Prometheus or Datadog, application logs, distributed traces, business events from Kafka, and security signals. Second, it must perform real-time feature extraction, converting raw streams into meaningful signals like rolling averages, rates, percentiles, seasonality components, and historical baselines. Third, it must run detection algorithms across the data, supporting both statistical methods like z-score and moving average, and machine learning methods like isolation forest, LSTM autoencoders, and clustering. Fourth, it must support multiple types of anomalies: point anomalies, contextual anomalies, and collective anomalies across univariate and multivariate time series. Fifth, it must provide alert management with severity, routing, suppression, aggregation, and root cause context so operators can act quickly without drowning in false alarms. Now the non-functional requirements. The system must be truly low latency, detect anomalies and fire alerts within seconds to minutes of the event occurring. It must be scalable, handling millions of metrics per second from thousands of services in tens of thousands of dimensions. It must be accurate, balancing precision and recall to minimize false positives and false negatives. It must be highly available, because the anomaly detection system itself becomes critical infrastructure during an outage. The system must also be adaptive, automatically adjusting to changing traffic patterns, seasonality, and new service rollouts. Finally, it must be explainable. Operators need to understand why a data point was flagged, not just receive a black box alert. Here is the high-level system architecture. Data sources on the left push metrics, logs, events, and traces into a high-throughput ingestion layer. Kafka is the central nervous system, partitioned by metric or service, feeding multiple consumers. A Flink or Kafka streams processing layer performs real-time feature extraction, windowing, and enrichment with historical baselines. The feature vectors are consumed by an inference layer that runs statistical detectors and ML models. Results are stored in a hot state store for dashboards, and an alerting engine that routes notifications based on severity and ownership. A batch model training pipeline periodically retrains ML models on historical data stored in a data lake or warehouse. A configuration service stores detection rules, thresholds, and routing policies. The user interface visualizes anomalies, overlays them on time series charts, and supports alert triage and feedback. The key metrics to memorize: cold detection latency, the time from an anomaly occurring to an alert being fired. False positive rate, the percentage of alerts that are not real anomalies. False negative rate, the percentage of real anomalies that are missed. Mean time to detect, the average time it takes to surface an issue. Precision and recall, the classic ML trade-off. Alert volume, total alerts per day, and alert signal-to-noise ratio, which is critical for operator trust. Model drift, how much model behavior changes over time as traffic patterns evolve. Query latency on the dashboard, because analysts need fast drill downs. And cost per million metrics processed, which keeps the economics of the system in check. These metrics are what the business and engineering teams actually care about. Let's trace the end-to-end user journey. A site reliability engineer at a streaming company is on call for the video playback platform. The anomaly detection system flags a spike in buffering ratio for a specific region and device type. The engineer opens the dashboard, sees the anomaly overlaid on a time series graph, and notices correlated signals. CDN origin latency is rising, rebuffer rate is climbing, and error logs show timeouts. The system suggests a likely root cause and routes the alert to the CDN team. The engineer acknowledges the alert, the system suppresses related notifications to avoid spam, and the team rolls back a bad configuration change. Within minutes, the metrics normalize. The anomaly detection system not only found the issue, but also helped triage and reduce mean time to resolution. The core models and algorithms. Statistical detectors use z-score, moving average, exponential smoothing, and seasonal decomposition to flag deviations from expected ranges. These are fast, interpretable, and work well for univariate metrics with stable baselines. Machine learning models like isolation forest, one-class SVM, and LSTM autoencoders capture complex, multivariate, and nonlinear patterns that statistics miss. Feature extraction transforms raw series into rolling means, percentiles, rates, Fourier components, and embeddings. Ensemble scoring combines multiple detectors and assigns confidence. Alerting thresholds apply dynamic or static cutoffs, with suppression rules and routing based on ownership and severity. The central trade-off is sensitivity versus specificity. Aggressive thresholds catch more issues but create alert fatigue, while conservative thresholds miss subtle but critical problems. Feedback loops let operators label false positives and retrain models. Now the low-level design deep dive. The ingestion layer writes raw metrics into Kafka, partitioned by metric name or service ID for horizontal scalability. A Flink job reads from Kafka, maintains tumbling and sliding windows, and computes feature vectors per metric. These features are joined with historical baselines stored in a stateful store or key-value cache. The inference engine runs both lightweight statistical detectors and heavier ML models, possibly on separate pools to isolate latency. An anomaly event table stores every detected anomaly with fields like metric ID, timestamp, severity, score, model used, and feature snapshot. The alerting service evaluates anomaly events against routing rules and suppression windows, then sends notifications. The configuration service stores detector rules, threshold policies, and ownership mappings. The training pipeline runs in the background, fetching historical windows from a data lake, retraining models, and publishing updated artifacts to model serving. Key takeaways for your interview. First, real-time anomaly detection is a pipeline problem. Ingestion, feature extraction, inference, alerting, and feedback loops all matter. Second, always distinguish between statistical and machine learning detection, and know when each is appropriate: statistics for speed and interpretability, ML for complex multivariate patterns. Third, false positive management is as important as detection itself. Mention suppression, aggregation, routing, and operator feedback. Fourth, latency and scale are hard constraints. Highlight stream processing, partitioning, and approximate algorithms where necessary. Fifth, explainability and context matter. An alert without a timestamp, feature snapshot, and correlated signals is not actionable. If you can walk through this system with these 5 points and mention real examples like Netflix detecting stream quality issues, Uber monitoring trip and pricing signals, and LinkedIn watching engagement and infrastructure metrics, you will signal strong senior-level design thinking. That's it for the Real-Time Anomaly Detection System. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the Real-Time Anomaly Detection System. We covered the full picture from Kafka ingestion and Flink stream processing, through feature extraction, Z-score, isolation forest, LSTM autoencoders, alerting, and the low-level design of the anomaly event table and pipeline. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.